All had a very busy stage, coming here at 9:30 and being here till 6. And I know many of you also had seminars, etc. in the night, discussions. And therefore, I think it's a good opportunity to go out tomorrow. Unfortunately, because of the President or the Prime Minister coming to Allahabad, that has become a little complicated, but many people are planning to go to Banaras, and a bus has been arranged. And Dipendu, he is the in charge of that bus. So I think the bus has been organized by HRI already, but it is to be paid for going. I think the bus capacity is 35. 35 people can go in the bus. And I think we cost about 500 to take the bus. Yeah. And we go in the morning. Yeah. I think people wanted to go rather early in the morning, perhaps because they wanted to take a train at 6 o'clock. It is perhaps not necessary to go that early, but it is only because I don't like to go that early. No, but I am not coming. The bus, from what I understand, will come to HRI at 4 in the morning, and it will go to all the hostels and places where people are staying. But maybe Dipendu can get some feelers from everyone about roughly when they want to leave. I think going to Banaras is not a problem because I think the Prime Minister will come to the city. Yeah. He is going, and I think about 15-20 people were already planning to go. But since the bus is now organized, more people can go. I think 35 seems like a good number. All right. So the purpose of my talk is to not tell you about anything new, but rather to give some kind of a tutorial on what had happened in the week, maybe taking a few concepts and doing a few examples of those concepts. So that in case you have been lost about discrete series, cusp forms, tempered representation, rank G equals rank K, you can see some of it and at least know what they roughly meant. So, yeah, so I think there were many lectures on representation theory of real groups. That is what we think of as a main body of work. But then there were also many lectures on automorphic representations, in which also he made some contributions. And then there were lectures on D modules and cohomological induction. Those lectures were requested in the hope to bring you to what the modern users are using. So I think there was quite a body of work which was surveyed. So I think one of the main concepts that comes up in theory of automorphic form is the notion of a cusp form. Notion of a cusp form. This was introduced for automorphic representation, and I know many of you may not be so much interested in automorphic representation, but maybe only interested in real groups or PRD groups or finite groups. But somehow this notion has interests. It originated in theory of automorphic form, but it is all pervasive. And in fact, this is one of the philosophies that was, I think, very much proposed by Harishchandra, the philosophy of cusp forms. To think of cuspidal representations which are contained inside tempered representations. and they themselves are contained in what are called admissible, irreducible admissible relations. So for real groups, these don't exist for real groups, and the one begins there, and one might say that for groups of finite field, there is nothing called tempered representations. Okay, so we had one of these, the main theorem of this program, discrete series exists defined only if rank G equals rank K, and I just want to give you a few examples for you to keep in mind what that means. So the main example that I will use for this lecture is G is equal to GLN R. So this group has a bit of center. For many purposes, it is just as well to look at SLNR, which is better in many ways. It is connected Lie group and the center is finite. So suppose we look at SLNR. So the rank of this group is equal to n minus 1. And the maximal compact in this case is SONR. And the rank of that group is rank of K is equal to n by 2, the integral part. So the rank that one was talking about here, one might as well call the rank of GC, and rank here could be called rank of KC. And therefore, discrete series exists. Discrete series exists if and only if SLNR as n equals 2. So, I think that is often the case that the groups that you most care about are not the right groups for many concepts. Meaning you have to do more work. So, GLNR doesn't have discrete series beyond n equals 2. So some other groups which do have discrete series and which are very popular in mathematics are groups like the unitary groups UPQ. They came up certainly in lectures of Arvind Nair, and just to define them, these are defined by Hermitian forms mod Z1 square plus mod Zp square minus mod W1 square, mod W2 square, and so on, mod W2 square. So this is the unitary group PQ, and okay. So if P plus Q equals n, then the rank of UPQ equals n. So one says that this UPQ is a form of GLN, but it is a friendlier form of GLN for purposes of discrete series. So what I am saying is that UPQ over complex number is nothing but GLNC. So its rank is n, and the maximal compact of UPQ is equal to UP cross UQ, and rank of UP is P, and therefore rank of K in this case equals P plus Q equals N, and therefore rank G equals rank K. So these groups have discrete series. There is another important invariant associated to discrete series representations. There is this group called WG mod WK. So this also could be just treated as WGC or WKC. This is W of GC or W of KC, and therefore this group is Sn upon Sp cross Sq, and the cardinality of Wg mod Wk is equal to factorial n upon. So yeah, this WG mod WK certainly would have made its appearance in parts of these lectures. Sorry?
SP2NR
Yes, SP2NR somehow I am not sure whether SP2NR came up in these lectures, so I used UPQ, but okay, SP2NR is the symplectic group. The symplectic group. And this is a group of rank n. Rank G equals n, and in this case, K is the unitary group UN, compact UN, whose rank is equal to rank K equals n. So, in fact, both UPQ and SP2N have many further present properties. They are what are called Hermitian symmetric spaces. They give rise to Hermitian symmetric spaces, and that has some utility. Okay, so people who are used to finite groups and periodic groups, they usually begin with cuspidal representations, and then they build tempoid representations from discrete series. Okay, so yeah. So the next thing I want to talk about is called parabolic induction. This is kind of one of the most used constructions, parabolic induction, and this is denoted by induction from P to 0. So P is a parabolic subgroup, rho is a representation of M, so this P is equal to Mn, and rho representation of M. So this is called parabolic induction, and it has many pleasant properties. We will note here that it takes representations of finite length to representations of finite length, representations of finite length of M to representations of finite length of G, length of G, and for many purposes it's also very important to know that it takes unitary representations to unitary representations. Sorry? which there are so many representations which are indistinguishable in many ways. This is these are discrete series. Often they come together. They are twin brothers of each other.
You are nowadays.
So they
You are nowadays mentioned in this context. You don't start with the game.
okay. Yes. Sure. No, indeed. So he played some very important role. Yeah. So parabolic induction has these two properties, and in the last lecture of Milichik, he mentioned that every representation is a subquotient of parabolic induction. Every representation of, let's say, GL and R is subquotient of a principal series induced from a character of the model. From a character of B, which is this group. Zero is here and it starts there. This is the group of upper triangular matrices. So any representation is embedded inside that. And one might think that it's therefore maybe there is not much to the subject. I mean, you have a principal series representation which is of finite length. Typically it is useful, and everything is sitting there, but somehow this picture is much too complicated. And I am not sure even now there is an understanding of this question even for a simple group like GLN. So one knows all irreducible representation in a very simple-minded way for GL and R. But what does a principal series representation look in terms of those irreducible representations is not understood. So a common word which is which is suggested at this point is that it is related to Kasdan-Lustig theory. So decomposition of principal series continues to be an important and difficult problem, both for real groups and for PRD groups. For finite groups, I think Lustig has done anything that can be done. So I think finite groups are understood, but not reals and PRDs. Okay. So, all right. So as I said, for GL and R, there are no discrete series, and these are the principal series, and all the other representations that we may be interested in are somehow coming out of these principal series in some ways, complicated ways. So, okay, so let me talk about tempered representations. But let me just say that discrete series representations are by definition unitary. So this we need to carefully keep that in mind, because the way discrete series representations are defined, this is somehow related to matrix coefficient mod fg square dg by dz, on G mod Z. And one wants their central character to be unitary so that this mod FG square makes sense, and this is infinite. So whenever we talk about discrete series or tempered representations, are also these are also unitary representations. And yeah, so I think they must have been defined during the course of these lectures. I'm not sure what is the official definition of tempered representations, but I mean, theorem G reductive group, and P a parabolic subgroup, of G with P equals Mn, and suppose phi is a discrete series representation of M. So it is a unitary representation. Then induction from P to G of phi. So because of that second statement there, that it takes parabolic induction takes unitary representations to unitary representations. This is a unitary.
Random decomposition of P we have.
But I am not taking Langdon's decomposition, I am just taking P equals Mn, and at the moment I am not twisting it. I am just taking P. A is there, but I am calling Ma to be M. Levy decomposition.
But we don't have discrete series.
That will have a discrete series in the sense that G mod Z will have a discrete series.
Oh, okay. Oh,
Yeah. So the discrete series have unitary central character. They exist on a group like G and U R. At the moment, I am assuming that phi is a discrete series, so we need cuspidal parabolic. So then I said that this is a unitary representation and finite length. And then by standard property of unitary representation, if you have a submodule, then you can look at the orthogonal complement to construct another module, and therefore it is completely reducible. So this is a direct sum of irreducible unitary representations. Of G. And these are all kind of statements, and the theorem which this theorem is supposed to say is that a representation is tempered if and only if it arises in this fashion.
Isn't tempered also defined as the matrix coefficient
2 plus epsilon, but I am
stop.
yeah, but we are not bringing much services. I mean, this is the theorem which one might be interested in from the point of view of parabolic inversion. So the main part of the theorem is that irreducible tempered representations arise uniquely So the tempered representations are what going into the Plancherel theorem as has come up in these lectures many times, and therefore to understand the tempered representation, all that one needs to do is to understand those parabolic subgroups which have discrete series, and just do this parabolic induction, and you are home. Okay, so the other thing which came up a lot is compact cartons, and more generally the collection of carton subgroups up to conjugation by GR. Somehow this is the set which controls the Plancherel theorem. Okay, so let us see what that set is for GLNR and what that means. So, so let us say carton subgroups in GLNR are of the form C star to the power D cross R star to the power n minus 2D. So this is not something which has been discussed here. It is some generality for all fields. And I let you think about it. This is just a diagonal entries, and these are those 2 by 2 block diagonal matrices which came up in Irwin's talk when he wrote A, B minus B, A. So this is isomorphic to C star, and these are the block diagonal matrices, and any carton subgroup in GLNR is conjugate to this subgroup. Okay, so the way the Plancherel theorem is built out of a discrete spectrum is H equals T times A carton subgroup. So you know, which is theta stable. I think in Irwin's talk, he certainly mentioned this observation that any carton subgroup in GR is conjugate to a theta stable carton subgroup, and that is perhaps a bit more convenient, but in any case, I have written down on the carton subgroups and they are all theta stable, so no issues there. So then what one does, one looks at M to be the centralizer of A in G. So centralizer of a torus is always going to be a Levy subgroup, and let P be a parabolic subgroup. With this as the Levy. As the Levy subgroup. There is a subtle point in the theory that although the subject is called parabolic induction, but it doesn't depend much on the parabolic. It depends more on the Levy subgroup. And it is source of a lot of complications in the subject. And these things have come up in lectures of Sandeep Verma and so on, intertwining operators and analytic continuation and whatnot. I think topics on which Harishchandra spent quite some time and effort. And they continue to be difficult topics, and so let P be a parabolic subgroup with this as the Levy subgroup, and therefore in our case, this Levy subgroup M will be just so it will be GL2R raised to power D cross R star raised to power n minus 2D. So what is happening is that this decomposition, this A is supposed to be the split torus, and the split torus is sitting there R star, and it is sitting here as R star, which consists of the scalar matrix A. So when you look at its centralizer in 2 by 2 matrices, scalar matrices, its centralizer is GL2, and therefore the Levy subgroup is GL2R to the power D cross R star. And this is the Levy, and what we are supposed to do is that theorem L2G is direct sum of L2G parameterized by H, where L2G H is direct integral of pi lambda means pi lambda star d lambda, and now this is on so there is a bit of the Lagrange decomposition which Professor Prasad was talking about. This M contains T times A, and A is supposed to be the connected component of the split torus. And it is that character group that I am talking about there. And this is sum over the character group of T. And that is the natural measure. So, okay, so where pi lambda, so this capital T is, maybe I have to take some part of T also inside here. Characters of capital T will give rise to discrete series representations of GL2R raised to power D. You know, this capital T is S1 to the power D. Each of those S1s will give rise to the maximal compact torus inside SL2R, and then there is a little bit of R star which will come from there, and together we will have a discrete series representation on this non-semi-simple group with the unitary central character. And so this T hat times A hat is to be treated as the character group of H. H hat is T hat times A. Okay, so somehow I wanted to show you all the Cartan subgroups and the relevant parabolic subgroups and the relevant planetary decomposition. And this pi lambda is supposed to be induction of a discrete series from that Levy subgroup to GL and R, where I lambda is induction from P to G, which is GLN R of let's say small phi lambda, which is supposed to be a discrete series representation of this Levy subgroup, which is GL to R to the power D times R star raised to power n minus 2. So you know it is besides some central subgroups, it is GL2R or SL2R. You use that discrete series on SL2R or GL2R, multiply by all unitary characters on the rest of the central factors, and use that to construct a representation I lambda, which is moving in a family parameterized by a head. Okay, so this is totally explicit, and this is what is the aim of the subject, and in some sense, once one understands discrete series, then the rest of the representations which figure in the Plancher's theorem is supposed to be straightforward. Okay, so the next remark. No. Yeah, okay, so maybe I think I have a lot more review material, but I see that I have some prospects also. So I want to talk about a little bit of new matters. But before I do that, I wanted to make a small comment about central infinitesimal character. It is something which confused me all along, all the time. Till I think Gordon Sabin told me what it is all about. Yeah. So you know, if one is looking at the group like GL and R, so I want to make a remark about central characters, infinitesimal characters.
Here in the last one, phi lambda is the representation of P to GL of phi lambda.
Pi lambda is a pi lambda star, where inside it is small pi lambda and outside it is somewhat bigger pi lambda.
That is the representing character of
It is a Levy subgroup which is product of GL2Rs and R star, and the kernel of that Levy subgroup is SL2R to the power D, where small pi lambda sets, but you have to thicken it with the central character, and that is the representation of M. And then it is moving in a family, and that is the whole family which needs to be plotted. And it is a fact that for GL2R, induction of a unitary representation is always reduced. So there is no reducibility problem. Induction of a unitary representation for GLN, parabolic induction takes reducible reducible. Okay, so some remarks on infinitesimal characters. Remarks on infinitesimal character. So, you know, this is something which is very abstract theorem of Harishchandra, that if you have a representation, then the center of the enveloping algebra operates via a scalar, and that scalar is some character on the Cartan subgroup and so on. So the question is, what does it mean? So if you take induction from B to, let's say, GL and R of a character chi, then chi is a character from R star to the power L to C star. So chi is bunch of n characters. So what does a character of R star look like? a character of R star is plus minus 1 times R plus, and R star is plus minus 1 cross R plus, and this infinitesimal character is supposed to retain the information only about numbers. So maybe I state it in two steps. Theta 1, all irreversible subcosines of a principal series have the same infinitesimal character. Infinitesimal character, and 2, so call this induced integration per chi, and this chi is an arbitrary character. So infinitesimal character of pi chi equals infinitesimal character of pi chi prime if and only if chi is equal to chi omega equals chi prime on R plus to the power. So, sorry,
Why do chi omega
is y. So this allows you to, okay, so in fact I made a question which must be well known, so I thought I will post that question. So there are certain equivalence on representations. Equivalences one can define on set of irreducible representations. So one is that they belong to principal series which share an irreducible component.
What is the if and if condition of the character?
Sorry.
If and if condition of the character, what is that?
This one,
The last.
this is a theorem I said.
Yeah, what is the condition?
Chi W is the wild conjugate of the character. So you know chi 1, chi n, and you can permute that. And 2 is xi of I1, I2 is non-zero for some i. And 3 they have the same central character and infinitesimal character. So okay, the meaning of this equivalence relation is that, you know, if you have a binary relation, then a binary relation can always be turned into an equivalence relation by saying that pi 1 is equivalent to pi 2 if there is a binary relation which goes from pi 1 to, no, if pi 1 is equivalent to pi n, if pi 1 is equivalent to pi 2 to pi 3 and so on, pi n minus 1 to pi n. So there are these three equivalence relations, and I feel that is the same set. Equivalence classes are the same. So question: equivalence classes defined by 1, 2, 3 are the same. Classes defined by 1, 2, 3 are the same. I mean, yeah. So in any case, part of my lecture now was supposed to be a review and summary of what was happening in the lectures, and partly I want to say something about what is going on in the subject for the moment. So I guess I started at 5:10 or 5:05. I think the previous lecture ended at 5:05, so I started at 5:10. So okay. So there is a subject which is growing, which is called relative representation theory. So relative representation theory. Yeah, I forgot to mention that the reason why I brought about that infinitesimal character was partly to explain to you that it is something very concrete, partly to tell you about this question, and partly to also say that those representations are destroyed followed by looking at their central characters. A direct calculation with the central character which I could have done in front of your eyes will say that those representations have different central characters. So there is no way they could be anything in common. Chan, you are following me? Okay, so the relative representation theory. So, you know, I mean, the relative representation theory has a subgroup H contained in G, subgroup, maybe a closed subgroup, closed, and basically the question is what is called the branching laws. Question: how do representations of G decompose when restricted to H? So, you know, this is a classical question which can be studied in the context of finite-dimensional representations of algebraic groups, which Sagar studied and two of my students here studied finite-dimensional representations of groups like GLN. And somehow the question is, how do they decompose if you restrict from GLN to GLN minus 1 or GLN minus 2, or from GL2n to SP2n or to SON and so on. So one might say that somehow one might say that wide character formula is one and the only one theorem in all of compact D group of algebraic representations of reductive groups, but it doesn't mean that it can solve all the problems. And I think it is famously said about Littlewood, Richardson rules that they were formulated long time ago and they were used to send the man on the moon, but they were proved only after the man. So this is what one can study in many contexts. H could be a subgroup which is reductive, and I know there are many many students here who are also interested in unipotent groups, and it's a very fertile area because instead of one group G, now we have a pair of groups. So there is a lot. And questions of this kind can be also interpreted in trying to understand diagonal H sitting inside H cross G. And if you have a representation phi 1 here and a phi 2 here and a tensor product and maybe dual here, then this Hom space diagonal H is non-zero if and only if phi 1 to phi 2 is non-zero. So this question about decomposition is maybe can be interpreted that there is a bigger group and a smaller group, and you are looking for the trivial representation. And the Frobenius list. So we have a bigger group which instead of G cross H, I will call it G, and smaller group diagonal H, which I will call it H, and the equivalent question we studied is when question given G comma H, how to understand Hom phi comma C. So by Frobenius reciprocity, one has equivalent formulations of this question in finite group theory that Hom G of phi C infinity functions on G mod H is equal to Hom H phi comma C, and this is isomorphic to Hom phi induction from H to CC infinity G mod H phi. Maybe there is a phi here. So there are these 3 points of view to understand this question. And both these points of view are closely related to L2. So, thus we are trying to understand L2 of G mod H with G and H at the bottom. And this is a G module, and there are many possibilities for G and H. And the work of Harishchandra in this context will be an example of this context. So all the work will become one example in which one looks at G cross G and the diagonal G, and L2 of G cross G upon the diagonal G is isomorphic to L2 G, and its spectral decomposition and its representation theory is what we have been learning in this program. And the more general question L2 G mod H has been studied for a long time. So natural decomposition. Natural decomposition has been studied for a long time. So I think there are many people from Scandinavian countries, from Japan, and okay. So this L2 of G mod H has been studied in two contexts greatly. One is when H is the fixed points of an evolution, of an involution, which is the case in the group case, G cross G upon diagonal G, there is an involution on G cross G which permutes the two factors whose fixed points is G. And this case seems analogous to this case, and this has been studied for a long time. And I think I have not been able to understand exactly how much has been understood and not understood, but there is a plancherel theorem for L2G mod S for symmetric spaces. But if I wanted precise information about multiplicities and what representations appear and which ones are tempered. So in this relative context, there is a notion of relative cuspidal, relative discrete series, relative tempered, relative matrix coefficients, and one can ask whether L2G mod H consists of only discrete series representations or tempered representations, and so questions of this kind have been investigated greatly over the years, and Patrick Delorme is one of the main leaders in that subject of understanding G mod H for symmetric spaces. But I think his might be culmination of many work from Scandinavian countries. Slitkrull is one of the names who proved an analog of Alexander's theorem about rank G equals rank K for symmetric spaces. There is a nice and neat condition when it should have a discrete component. But that discrete component need not be a discrete series. And yeah, so there is this case, but so Delorme will be here in the conference next week, and I should say that I would say that the subject of symmetric spaces perhaps gives rise to related subject of spherical varieties, which are more general than symmetric spaces. Spherical varieties, and there has been a great work, I think one of the most fundamental works in this subject for many decades, and that is due to Sakellarides and Venkatis. So they have, I cannot understand what they have proved, but in any case, they have studied this problem and they have formulated a plancherel theorem for L2G mod H in great generality. And one of the points of view is that L2G mod H looks like a spectrum of some other group. So L2G mod H looks like L2 of G prime. And yeah, so Sakellarides will be here next week, and yeah. Okay, so that is all. And thank you.